In most modern electrical systems, the neutral and ground are bonded together at the transformer or main service panel. This is done to ensure that the neutral remains at zero potential and provides a safe path for fault currents. However, bonding the neutral and ground within a control panel can create a potential hazard. If a fault occurs in the control panel, current could flow through the bonded neutral and ground, bypassing the circuit protection devices. This could result in electrical shock or a fire. For correct wiring, run the 3 phases and the neutral to the control panel. Connect the neutral to the neutral terminal on the control panel. Connect the ground to the ground terminal on the control panel. If the control panel is connected to other equipment that requires a bonded neutral and ground, such as a transformer, bonding should be done at the transformer or main service panel, not within the control panel. Always follow the manufacturer's instructions for the control panel and consult with a qualified electrician for any wiring work. The reason is to ensure electrical safety and proper function of circuit protection. Bonding neutral and ground at multiple points creates parallel paths for neutral current. This can lead to several problems. Firstly, ground loops can occur. Ground loops are undesirable current paths that can introduce noise into sensitive electronic equipment. This noise can interfere with the proper operation of the equipment, causing malfunctions or inaccurate readings. Secondly, elevated ground potential can occur. When neutral current flows through the ground conductor, it can raise the potential of the ground relative to the earth. This elevated ground potential can create a shock hazard if someone comes into contact with both the grounded equipment and another grounded surface. Thirdly, nuisance tripping of ground fault circuit interrupters can occur. Ground fault circuit interrupters are designed to detect small imbalances in current between the hot and neutral conductors. If neutral current is flowing through the ground conductor, it can cause the ground fault circuit interrupter to trip even if there is no actual ground fault. The correct method is to maintain a single point of bonding. The neutral and ground should only be bonded together at one point, typically at the service entrance or transformer. This ensures that all neutral current flows through the neutral conductor and that the ground conductor is only used for fault currents. To properly connect the control panel, firstly, isolate the control panel. Ensure that the control panel is de-energized before beginning any wiring work. Secondly, run the conductors. Run the 3-phase conductors, the neutral conductor, and the ground conductor from the source to the control panel. Thirdly, connect the phase conductors. Connect the 3-phase conductors to the appropriate terminals in the control panel. Fourthly, connect the neutral conductor. Connect the neutral conductor to the neutral terminal in the control panel. Fifthly, connect the ground conductor. Connect the ground conductor to the ground terminal in the control panel. Sixthly, verify the wiring. Double-check all connections to ensure that they are tight and correct. Use a multimeter to verify that there is no continuity between the neutral and ground conductors in the control panel. Note that the National Electrical Code, or NEC, addresses grounding and bonding requirements in Article 250. 4, 20, 24, 28, 30 and 50 specifically address grounding and bonding requirements for services, separately derived systems, and other electrical equipment. Always refer to the latest edition of the NEC for the most up-to-date requirements. Also, local codes can vary. Always check with your local electrical inspector to ensure that your wiring complies with all applicable codes and regulations. And remember to consult with a qualified electrician. If you are not comfortable working with electricity, always consult with a qualified electrician. Electrical work can be dangerous, and it is important to take all necessary precautions to avoid injury or property damage. The purpose of grounding is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protection devices such as circuit breakers or fuses. When a fault occurs, such as a short circuit between a hot conductor and ground, a large current will flow through the grounding system. This high current will quickly trip the circuit breaker or blow the fuse, interrupting the flow of electricity and preventing damage to equipment or injury to personnel. Grounding also helps to stabilize voltage during normal operation. By providing a reference point at zero potential, the grounding system helps to minimize voltage fluctuations and transients. This can improve the performance and reliability of electrical equipment, especially sensitive electronic devices. Bonding refers to the connection of all non-current carrying metal parts of an electrical system to create a continuous electrical path. This includes equipment enclosures, metal conduits, and other metallic components. The purpose of bonding is to ensure that all metal parts are at the same potential, minimizing the risk of electric shock. Bonding also provides a low impedance path for fault current to flow back to the source. This helps to quickly clear faults and prevent the build-up of dangerous voltage levels on metal parts. The size of the grounding and bonding conductors is determined by the size of the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the ampere rating of the circuit breaker or fuse. For example, NEC Table 250.122 provides guidance on sizing equipment grounding conductors for alternating current circuits. It is important to use the correct size of grounding and bonding conductors to ensure that they can safely carry the fault current and provide a low impedance path back to the source. The material used for grounding and bonding conductors is typically copper or aluminum. Copper is the preferred material due to its excellent conductivity and corrosion resistance. However, aluminum is sometimes used for larger conductors due to its low cost and weight. When using aluminum conductors, it is important to use connectors that are specifically designed for use with aluminum to prevent corrosion and ensure a reliable connection. The location of the grounding electrode is typically at the service entrance of the building. The grounding electrode is a metal rod, pipe, or plate that is buried in the earth and connected to the grounding system. The purpose of the grounding electrode is to provide a connection to the earth, which serves as a reference point for the electrical system. The grounding electrode helps to stabilize voltage and provide a path for fault current to dissipate into the earth. The type of grounding electrode used depends on the soil conditions and local codes. The NEC specifies the requirements for grounding electrodes in Article 250.50 through 250.70. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. Ground plates are typically made of copper and are buried horizontally in the earth. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Separately derived systems, such as generators or transformers, require their own grounding and bonding systems. The grounding and bonding of separately derived systems is similar to that of service entrances, but there are some important differences. The neutral conductor of a separately derived system must be bonded to the equipment grounding conductor at the source of the system. This bonding connection must be made at the transformer or generator, not at the distribution panel. The size of the grounding and bonding conductors for separately derived systems is determined by the size of the transformer or generator. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the kilovolt-ampere rating of the transformer or generator. Ground fault circuit interrupters are designed to protect people from electric shock. They work by detecting small imbalances in current between the hot and neutral conductors. If the difference in current exceeds a certain threshold, typically 5 mA, the ground fault circuit interrupter will trip, interrupting the flow of electricity. Ground fault circuit interrupters are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. They can be installed in circuit breakers or receptacles. Arc fault circuit interrupters are designed to protect against fires caused by electrical arcs. They work by detecting the unique characteristics of electrical arcs, such as the high-frequency noise and irregular current waveforms. When an arc fault is detected, the arc fault circuit interrupter will trip, interrupting the flow of electricity and preventing a fire. Arc fault circuit interrupters are required in many locations, such as bedrooms, living rooms, and dining rooms. They are typically installed in circuit breakers. Surge protective devices protect electronic equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. Surge protective devices work by diverting the excess voltage to ground, protecting the equipment from damage. Surge protective devices are available in a variety of types, including whole house surge protectors and point of view surge protectors. Whole house surge protectors are installed at the service entrance of the building and protect all of the electrical equipment in the building. Point of view surge protectors are plugged into individual outlets and protect the equipment that is plugged into the outlet. Electrical safety is a critical aspect of any electrical system. It is important to take all necessary precautions to avoid electric shock and fire. Always follow safe work practices when working with electricity. Wear appropriate personal protective equipment, such as gloves and safety glasses. Energize circuits before working on them. Use insulated tools. Inspect electrical equipment regularly for damage. Replace damaged equipment immediately. Never overload circuits. Use extension cords safely. Do not run extension cords under rugs or furniture. Do not use extension cords as a permanent wiring solution. Keep electrical equipment away from water. Install ground fault circuit interrupters in areas where there is a high risk of electric shock. Install arc fault circuit interrupters to protect against fires caused by electrical arcs. Use surge protective devices to protect electronic equipment from voltage surges. If you are not comfortable working with electricity, always consult with a qualified electrician. Electrical work can be dangerous, and it is important to take all necessary precautions to avoid injury or property damage. Electrical systems are governed by a complex set of codes and regulations. These codes and regulations are designed to ensure the safety and reliability of electrical systems. The National Electrical Code is the most widely adopted electrical code in the United States. The NEC is updated every 3 years to reflect changes in technology and safety practices. Local codes may also apply. It is important to check with your local electrical inspector to ensure that your wiring complies with all applicable codes and regulations. Understanding electrical schematics is essential for troubleshooting and maintaining electrical systems. Electrical schematics are diagrams that use symbols to represent the components of an electrical circuit and their connections. By studying an electrical schematic, you can understand how a circuit works and identify potential problems. Electrical schematics typically include symbols for components such as resistors, capacitors, inductors, transistors, and integrated circuits. They also include symbols for conductors, switches, and other wiring devices. The symbols are standardized to make it easier to understand the schematic. Electrical testing equipment is used to measure electrical parameters such as voltage, current, resistance, and continuity. Common types of electrical testing equipment include multimeters, clamp-on ammeters, and insulation testers. Multimeters are versatile instruments that can measure voltage, current, resistance, and continuity. Clamp-on ammeters are used to measure current without having to disconnect the circuit. Insulation testers are used to measure the insulation resistance of conductors and equipment. Electrical troubleshooting is the process of identifying and correcting problems in electrical systems. Electrical troubleshooting requires a systematic approach and a thorough understanding of electrical principles. When troubleshooting an electrical problem, start by gathering information about the problem. Ask questions such as what is the problem, what are the symptoms, when did the problem start, what has changed since the problem started. Once you have gathered information, use electrical testing equipment to measure voltage, current, resistance, and continuity. Compare the measurements to the expected values to identify the source of the problem. After the electrical issue is resolved, verify that the repair is working properly. Use electrical testing equipment to measure voltage, current, resistance, and continuity. Monitor the system for any signs of recurrence of the problem. Document the troubleshooting process. This will help you to remember the steps you took to solve the problem and will be useful for future troubleshooting efforts. Electrical maintenance is the process of keeping electrical systems in good working order. Electrical maintenance includes tasks such as inspecting equipment, cleaning equipment, tightening connections, and replacing worn parts. Regular electrical maintenance can help to prevent problems and extend the life of electrical equipment. Develop a preventative maintenance schedule. This will help you to ensure that all of the necessary maintenance tasks are performed on a regular basis. Keep accurate records of all maintenance work. This will help you to track the condition of your equipment and identify potential problems early on. Provide training to employees on proper maintenance procedures. This will help to ensure that maintenance work is performed safely and effectively. And lastly, it is important to keep the area clean and free of debris.